first. All right, and now we'll share screen. It takes me a minute to set this up, and I haven't done this for a while, so let's hope this works. Oh yeah, I have to install a plugin, wouldn't you know? It usually doesn't take very long. Every few weeks you have to install a new plugin. Okay, there we go. All right, good. All right, so let's do this here. All right, with any luck, that gives it to us. Enlarge this. Can you all see? Let me put this on lock screen. I'm going to turn on the light here because I think it may help a little bit. Hope that doesn't wash it out. All right. Can everybody see that all right? It looks fine on my screen. Okay, so I'm just going to lecture on this pad of paper like this. If you have any questions about the lecture, please feel free to interrupt me at any time. I'm glad to do that. I'm also glad to hang around for some minutes after the lecture is over for questions, if you have any at the end. I mean, if we were doing in-class lecture, I'd usually have a group of students come up to me afterwards with a lot of questions. So we can do the equivalent of that here. And also it'll have the advantage of getting on the recording. I'll usually have the recordings taken care of and posted on the website by the following day. So tomorrow, I'll try to get that done by then. In case you can't attend the lecture in what passes for in person here. All right, so the plan is that first of all, I'm not going to talk about logistics because that's all contained on the website. Please go to the website. Assume everyone has received an email by now with a link to the website. You're going to need to go to that website for homework assignments and other looking at notes and other purposes. So you'll be familiar with it before the semester is over. You need to use that. So go there. There's a complete description, I hope complete, of the logistics of the course. If you have any questions about it, of course, just send me an email and I'll clarify it or rewrite the website as needed. So I'm not going to talk about that tonight. What I am going to do is get started on the course. And I want to begin with some issues of mathematical methods that are used in quantum mechanics. We're going to try to take care of most of these at the beginning, in first lecture or lecture and a half. And then after that, we'll move on into the physical postulates of quantum mechanics that allow us to connect the mathematics with the physics. That's the general plan. In all of this, I'm assuming that you have at least a full year's experience with undergraduate quantum mechanics so that you know, generally speaking, the kind of thing that I'm talking about. This is not, in case anybody doesn't understand this, this course is not an introductory course. It's a second year course in quantum mechanics. We're going to, in 221A, review the material that you probably would have had in a full year of undergraduate quantum mechanics and also introduce a fair amount of new material. The review is going to consist of going over it again, but from a deeper and more organized standpoint. We're going to try to put it into some logical coherence using a sort of pseudo-axiomatic approach, which you'll see developing tonight. But then there's also going to be quite a bit of new material as well this semester. The second semester of the course will be mostly new material. It'll get into an introduction to quantum field theory and relativistic quantum mechanics, as well as scattering theory and other topics in the second semester. All right, so that's the plan. So I'd like to begin with the subject of Hilbert spaces. And so let me write that out, Hilbert space. A Hilbert space is a mathematical designation for a certain type of vector space. So let me list out the properties of it. It's a complex vector space. It is usually thought of as being an infinite dimensional space. To say it's a complex vector space means that when you form linear combinations of vectors, you get to use complex numbers as the coefficients of the linear combination. That's all it means. It also has the property of possessing a scalar product or a metric, which we can talk about this way, as AB is defined, scalar product of A to B is defined. A Hilbert space also has the property that the vectors of the Hilbert space are a finite norm. That is to say, if A is such a vector in the Hilbert space, and A scalar product with itself is finite, and I'll indicate that by saying it's less than infinity. In a finite dimensional vector space with a norm defined on it, all vectors are automatically a finite norm. But in infinite dimensions, you have an infinite sum, if you like, summing over the basis vectors. And so there's a question about whether the answer is infinite, and sometimes it may be. But a Hilbert space has only finite vectors of finite norm. A fifth property is a property of completeness. This is a topological property that people that take functional analysis and topology and so on learn about. It mostly won't concern us very much, but it has to do with the convergence of sequences. And this is important in establishing rigor about what you mean by operations in infinite dimensions, where you've got to deal with infinite sums and things of that sort. Now, the reason Hilbert space as a mathematical object, with very roughly speaking, this outline of definition, parts of the definition of it, the reason it's relevant for quantum mechanics is that the spaces of wave functions that we use in quantum mechanics actually are Hilbert spaces. This is modulo a few details that I'm glossing over, but that's the basic idea. And why do we care about that? Why don't we just go ahead and ignore the fact that they're Hilbert spaces? The reason is that there's two things that I want to convey here. One of them is that for most of the operations that one does as a practical quantum mechanic, certainly in this course, I'd say it depends on what field you go into, but for most of the operations you do, you can use vector space intuition that derives from finite dimensional vector spaces, and it will work. This means concepts of things like linear algebra concepts, like the notion of a span of a set of vectors, linear independence, basis states, basis vectors. Our vector spaces also have a scalar product defined, so you have notions of scalar product, dot product, if you will, orthogonality, normality, orthonormality of basis vectors, unit vectors, projection operators, orthogonal subspaces, all that kind of stuff comes in. And this provides a geometrical intuition. So let's talk about wave function spaces. Let's say I've got a space of wave functions psi of x for a quantum mechanical problem. This is a collection of those wave functions. As you know very well, this forms a vector space. It's a complex vector space because you can add wave functions together, basically. And it also has a norm in it, scalar product, which you all know about as well. And I think you also know that these geometrical concepts that derive from linear algebra of the space of wave functions is very useful in the actual calculations we do in quantum mechanics. All right. Now, so the first issue is that we can get by with a lot of intuition that comes from finite dimensional spaces. That's good because many of us, maybe I shouldn't speak for you, but many people, let's say, have had only an introductory course in linear algebra, and typically there they only deal with finite dimensional spaces. When you go to infinite dimensional spaces, the mathematics is considerably more subtle, and there are different types of infinite dimensional spaces. So the fact that it turns out that the one that we're interested in is a Hilbert space makes a difference here, because it turns out that one of the properties of Hilbert spaces as an infinite dimensional space is that many of the mathematical aspect properties of the space are the obvious generalizations of what you have in finite dimensions. So finite dimensional intuition actually works most of the time in infinite dimensions. So that's good for the purposes of doing quantum mechanics. It means, for one thing, you don't have to go take a course in functional analysis to do most quantum mechanics. All right. The second thing to say is that this linear algebra plus metrical structure in the vector space, as we will see when we come to the measurement postulates of quantum mechanics, we will see that those postulates are expressed purely in terms of that structure. They don't depend on anything else. What we'll also see is that the measurement postulates don't even refer to wave functions. They don't need to. They just talk about this linear algebra structure. That's all that's needed. Well, that linear algebra structure, if you're worried about infinite dimensions and the complications that induces, is properly referred to the mathematics of Hilbert space. All right, so that's roughly why I'm talking about it. All right, so spaces of wave functions are also vector spaces like this. So the spaces of wave functions in quantum mechanics are sometimes finite dimensional. This happens for spin systems. But if you have spatial degrees of freedom around, then they will be infinite dimensional. So infinite dimensional spaces of functions are very important in practice, and they are, modulo some small details, they are isomorphic to Hilbert spaces. Okay. Now, by the way, I don't want to talk about just arbitrary spaces of wave functions. I want to restrict the class of wave functions. Let's talk about wave functions that are normalizable. These are ones for which the integral over x of psi of x squared is finite, which I'll indicate by saying it's less than infinity. That ding dong is my email, and I would normally turn it off, but I want to leave it on in case somebody sends me an email having trouble. And the answer is no, that's not what this is. Let's see what I've got here. Anybody's having trouble. So the answer is no, that's not what that was. All right, so to go back to the point here is, let's talk about spaces of wave functions which are normalizable. This is important physically because a real particle has to be found somewhere in space with a probability of 1. And if you have wave functions that are not normalizable, that means that they're not physical. Physical wave functions are normalizable. On the other hand, as you know very well, we frequently deal in quantum mechanics with wave functions that are not normalizable. For example, an eigenfunction of energy of free particle is e to the ikx, and this does not represent a physical state because it has an infinite norm. It could be thought of as a kind of a limit or an idealization of a family of physical states, and sometimes that's useful to do, like a Gaussian wave packet whose dimensions keeps expanding until it fills up all the space. But these are by themselves not physical, in spite of their utility in their use in quantum mechanics. So, but the mathematical definition of Hilbert space requires the vectors to be normalizable, and so that's where I'm including. That's part of the reason I'm including this norm. But you see, this mathematical requirement corresponds nicely with the physical requirement of normalizability for physical states. All right, so those are spaces of wave functions. Now, it isn't quite true that a vector in the abstract Hilbert space corresponds to a definite wave function. I mean, it's true in a sense that spaces of wave functions are Hilbert spaces, but there's some details. And here is one of the details, that if I have two wave functions, let's say here's psi of x, here's psi, and here's x, and it's just a curve like this. Let's say I've got like that. And I have another wave function, which is the same, except that at one point I make a hole in the wave function and I lift the point up like that. So it's the same wave function, except at one point. These aren't the same wave functions, but they give the same answer when used under integrals. And it's only through the use of integrals, i.e. scalar products, that the physical results of quantum mechanics are expressed. And as a result, there is no physical difference between these two wave functions. They're exactly the same in their physical effects. And this is reflected in Hilbert space theory by the fact that a vector in Hilbert space does not actually correspond to a unique wave function, but rather to an equivalence class of wave functions which differ from one another by things like this. They differ on a subset of measure zero, as they say, or we say the two functions are equal, quote unquote, almost everywhere. That's the terminology that's used. Now, about this changing the wave function at one point, you might say, well, these can't be physically the same because I can go measure the wave function at the point x, right, and decide which of the two values it is, right? Right? Well, actually, that's not right. You can't measure a wave function at a point x. You can choose some region of space, some small region if you want, and you can do a lot of experiments on a system to accumulate statistics and find out how often your electron or particle lies inside that region and therefore get a probability. And if you do that, what you've got then is an integral of psi squared over that region, and you can determine that, you know what that is. But that's not evaluating psi at a point, it's only an integral of psi. And in fact, that's all you can do is evaluate integrals experimentally. All that can be determined is integrals of psi. In fact, it's integrals of psi squared, not just psi itself, it's psi squared. You can't even measure psi squared at a point because these two things have the same integrals. So this is why the mapping between vectors in Hilbert space in the mathematical sense and wave functions is not one-to-one. These are details we can gloss over for essentially all the purposes of this course, but I'm bringing it up in part just to show you some of the interesting connections. Actually, the mathematical properties of Hilbert spaces and some of these others I didn't mention do in fact correspond to physical aspects of the measurement process. All right. Now, anyway, so let's stop talking about Hilbert spaces for a while. Well, I guess I can't stop that, but let's move on to let's talk some more about wave functions. I'll put it down here towards the bottom of the page. You know that given a wave function psi of x in one dimension, there's a corresponding momentum space wave function phi of p, which is given by an integral, which is essentially a Fourier transform, which I'll copy for you here. It's e to the minus ipx over h bar times psi of x like this. This is essentially, apart from factors of h bar, it's essentially a Fourier transform. And that means that we can take any of the wave functions in our wave function space and carry out a Fourier transform on it and produce a momentum space wave function I'll call phi of p. And I'll leave a big bracket here for the set in question. I want to leave space here because the x space wave functions are, as I say, are supposed to be normalizable to be physical. And so there's got to be some condition on the momentum space wave functions as well. Well, it turns out the condition is that they're normalizable too. That's the same condition. And the reason this is because of the Parseval identity. I have to think how to spell it because it's not the same as the opera by Wagner. Parseval identity says this, is that the integral over x of psi of x squared is equal to the integral over p of phi of p squared, assuming that these two wave functions are related by the usual Fourier transform you see up above. The norm in one space is the norm in the other space. So the Hilbert space of momentum space wave functions here is this one. And these two spaces are related by the Fourier transform, which I'll call U. Fourier transform is an inverse, of course, which I'll call U inverse, goes back the other way. There's a mapping going back and forth between these spaces. And this is a one-to-one map. And what the Parseval identity tells us is that this is a map that preserves the scalar product. What that means is that the map, as we say, the map is unitary. That's why I called it U here. It's a unitary map between these two spaces. Now, unitary mapping preserves all of the Hilbert space structure, including the details here that I'm glossing over. And so these two spaces are isomorphic as Hilbert spaces. And given that the postulates of quantum mechanics are expressed purely in terms of that Hilbert space structure, it means that any calculation you do with a definite physical outcome with one of these spaces of wave functions can be mirrored in the other space of wave functions with no change in the answer. These two spaces are equivalent as far as doing physical calculations are concerned. Let's call this first space E sub x here, meaning Hilbert space of wave functions in the x representation. Call this one E sub p. You see these spaces are associated with physical observables, position, and momentum. You can also define a similar space involving energy, and it's got invertible unitary transformations and mappings between it and the other spaces, or other spaces as well corresponding to other physical observables. There's a whole family of these. These, as we say, correspond to different representations of the state of the system, the position, momentum, energy, and whatever representations of the system. Okay. And they're all equivalent, as I say, in terms of the mathematical operations you want to perform. Now, here's the question I want to pose at this point. It's really ultimately only a psychological question, but I want to kind of give you an attitude adjustment if you need it for the rest of the course. In this regards, wave functions. The question is this, is that which one of these spaces, if any, has any privileged role over any of the other spaces? Is there any argument you can make that makes one of them better than the other? And I think if you ask a lot of people that, they would say, well, it's obviously the psi of x because that's where the whole world of quantum mechanics begins, isn't it? You know, wave function psi of x, right? That's how I learned it in my first course. It's also certainly true historically, that's how the subject began, was wave function psi of x, what people thought about. But there isn't anything, as I keep saying, there isn't anything in the measurement postulates or the machinery of quantum mechanics that gives a preference on any of these spaces. So what is special about the psi of x? aside from the fact that's how we learned it. Well, you might say we live in X space, we don't live in momentum space. So X space is real space, right? How about that argument? Well, that argument kind of doesn't work so well when you push it a little bit, because it's true that we live in three-dimensional physical space, but the wave function is defined on three-dimensional physical space only in the case of a single particle moving in 3D. For example, if you have two particles, then the wave function is defined in the compound space with two coordinates x1 and x2. It's really a six-dimensional space. That space in question is what we call the configuration space of the system. That's where the wave function is defined. And that coincides with ordinary physical space only in the special case of a single particle in 3D. So it's not general. Well, you might say, let's just, okay, fine, but what about a particle in 3D? You know, then don't we have a field on real physical space? It's kind of like an electric or a magnetic field, or, you know, pressure of a fluid or something. It's like a field. It's a complex field to be sure, but, you know, what about it? Can't we measure it? You know, for example, can we measure it? Well, actually, the measurement of a wave function, even in this case where you got a particle in 3D, is a very tricky subject. And it isn't at all like measuring the pressure of a fluid where you have a pressure meter or temperature, you have thermometers and so on, where you can make, in principle, definite measurements. There is no such thing as a psi meter. And in fact, quote unquote, measuring the wave function psi is a tricky subject, and we'll see all the more as we go on why that's so. But I kind of already pointed out some of that, which is even measuring psi squared at a point is actually not possible. That even ignores the phase of the wave function. You can measure the average value psi squared over a region, that can be done. But then to measure the phase of psi, that's another whole issue, which it turns out can't even be done without a commitment to a gauge convention for the electromagnetic vector potential, amazingly enough. Otherwise, there's no answer. We'll see this coming up as we go into the course. So wave functions are quite different. They're not just like fields on ordinary configuration space. So I want to disabuse you of the notion that somehow psi is a God-given thing that lives on three-dimensional space, and that's where the whole story begins, because that's not the way it works, and that's not what is supported by the measurement postulates of quantum mechanics. And if you think that, you're going to be misled, and you're not going to be thinking about things at the most fundamental level that you need to think about in doing real work in quantum mechanics. All right. Now, given the fact that all these spaces are equivalent to one another and none has any privilege over all the other, it's a good idea to develop a notation which doesn't prejudice the choice amongst the spaces. And that's just what the Dirac-Bras-Ket notation does, and that's what I want to tell you about now. So what we do with the Dirac-Bras-Ket notation is we introduce yet another space. I'm not sure I have room for it here. We introduce another space. I'll just call it E without a subscript. And maybe I'll call it E sub state, because it's really what we'll call the state space or Ket space of the system. And it's the space consisting of what we call Ket vectors. And a Ket vector in the Dirac notation is indicated by a vertical line and a right angle like that. And we have to usually put some identifying symbol in it to distinguish it from other vectors. And so we'll call this psi here to put a symbol in it like that to indicate the state vector. And what this is that this is yet another Hilbert space, but that's how we'll look at it. It's an abstract space, which is distinct from any of these other concrete spaces of wave functions, but which is also isomorphic to all of them. So for example, there are rules that convert a vector in the Ket space or state space with a wave function psi of x. That's going to be another is really a unitary transformation, goes both ways. Here also there's connecting these other versions of these spaces as well. There's all of them, but yet we will regard this as being a distinct space. Many authors and lots of books and lots of literature don't do that. They write down psi like this, and what they mean by that is, oh, this is just another notation for the wave function. But I advise you not to do that. It's better to regard these as two different spaces, and then to regard the conversion from one to the other, and there's rules we'll give for that, as being a part of the isomorphism between these spaces. All right. Now, so that's the basic idea of the Ket space or the state space of the system. Now, this is a Hilbert space, and so it has all these properties. It's a complex vector space, infinite dimensional, usually infinite dimensional, scalar products defined. We wanted to be a Hilbert space, we want to talk about vectors of finite norm and so on. That's all assumed here, and just setting this up as a Hilbert space. We're going to deal with the physical postulates of quantum mechanics at a later probably the next lecture. Hopefully we'll get to it. But before I get into that, let me try to do this way. I'm going to move this down some so we can see a little bit about where we were, like that. Okay. By the way, is everybody seeing this all right? Is the writing big enough? I'm writing with a kind of a dull pen, which forces me to write larger than I might otherwise.
It's great.
Looks good here.
All right, good.
For the
Now-
cat space, what's the energy? What's the subscript under the energy?
It's not energy. E just stands for the space. I might call it H for a Hilbert space, but if I do, it confuses with a Hamiltonian. So that's all it means.
That makes sense.
Script
Okay.
E, right. Okay, yeah, here's what I want to say. So let's kind of just crudely speaking, visualize the Ket spaces by drawing axes like that. It's a vector space, okay? I want to deal at a later point in detail with the physical postulates of quantum mechanics, but I just want to say one thing right now, which is what you call a physical state. In fact, this has to be what you call a pure state, which we'll define later what that means. But a pure state corresponds to not a vector in the Ket space or the state space of the system, not a definite vector, but rather to what we call a ray. An array is the following. Array is basically a set of vectors that are all proportional to one another. So it's a set that looks like this. It's some constant factor or C factor multiplying a size 0, where C is any complex number. And size 0 is some element of the Ket space, which is not equal to 0. In other words, you just take some non-zero Ket vector and then you multiply by all complex numbers. And if I do that, so like, let's say here's the original Ket vector size 0. Then by multiplying by all complex numbers, you just scale it up and down, you see like this, and you create in effect a one-dimensional subspace of the overall Ket space, which is what this whole thing is here. So this is what the ray is. It's really a one-dimensional subspace of the Ket space. And the physical state corresponds to the ray, not to any particular vector in the ray. Now, this is just a way of saying that the normalization in phase of the Ket vector is of no physical significance. That's all it means. But in any case, I just want to mention that this is part of the physics, that the physics corresponds to rays, not to Ket vectors. By the way, we oftentimes I'll do this a million times before the semester is over, refer to size 0, for example, or some psi as the quote unquote state of the system. But it isn't really psi that's the state, it's the ray which is spanned by psi, which is the state. So this is abuse of language. All right. Anyway, that's just a mention about rays. Now,
sorry to interrupt.
That's all right.
So why did you say that the fact that you can scale in the ray, you can scale the vector to any amount? Why does that imply that the phase is of no particular significance?
Well, you probably know that it doesn't affect expectation values, but we'll see when we come to write down the postulates of quantum mechanics that the overall phase of a wave function and even its norm, its magnitude, don't matter for the physical outcome. The physical outcomes are independent of that. It's the ray which matters. I mean, in practice, we normally, for convenience, use normalized wave functions, but there's nothing that says you have to do that. And the physical outcomes don't really depend on that. Okay. Okay, so and by the way, when I set up these Ket spaces here, I required them to be normalizable. I didn't require them to be normalized. If you did, you don't get a vector space, for one thing. Normalizable vectors don't form a vector space. Their points live on the surface of a sphere. All right. Okay, so the strategy then is going to be, in the next several lectures, is to develop the geometry of the Ket space, ultimately connecting it with the measurement postulates of quantum mechanics. And then only after that is done, will we connect it with wave functions, which are up here. So I won't be talking about wave functions for the next couple of lectures, except insofar as I use them for purposes of illustration. So we want to concentrate now on the abstract Ket space and its properties. one of the things here is that if you have a wave function, let's say psi of x, as you know, it's easy to form its complex conjugate, and you need to do that to form scalar products. So there's a CC operation that does this. Let me move this up now. It sure would appear that the complex conjugated wave function is just another wave function, and it ought to belong to the same space of wave functions as the original one did. That actually is not such a useful point of view. In fact, it's better to regard the complex conjugated wave function as belonging to a different space, something which I'll talk about in a minute, is what we call the dual space. Because if you do this, this helps keep track of the different operations that one normally does. In fact, one seldom ever sees an expression in quantum mechanics where you've got a linear combination of a wave function and its complex conjugate. We don't do that very often. All right, anyway. On the other hand, our ket space is a set of just normalizable kets, and complex conjugation isn't defined on them. They're just vectors in a space. So how do we take care of the complex conjugation that we're going to need? The answer to this is I need to introduce the machinery of the dual space and also the metric which is in the ket space. So let me address those issues. If I have a vector space E like this, let's just call it E. We're thinking of ket spaces here. These contain kets. Then I want to define, which look like this, psi, like this is a notation for them. I want to define what I call a bra. And a bra is a map. By my definition today, a bra is a map, bra, which maps kets, which live in the ket space, into complex numbers. And it's required to be linear. So in words, for the time being, in fact, this is for the rest of the course, is a bra is a complex valued linear map that acting on kets. It's an operator that acts on kets and produces complex numbers. Now, in the Dirac notation, a bra is indicated by something that looks like that with an angle and then a vertical line. And just as in kets, we put identifying symbols in them like alpha or something like that to distinguish them from other bras. But a bra is not the same as a ket. It doesn't belong to the space E, rather it's a map from the space E into the complex numbers. Okay. Now, being a linear map means that if I let it act on a linear combination of psi vectors, you get the usual distribution law, but this is going to be alpha, this is going to be C1 times, oh, let's see, before I go into that, let me just say something here about notation. I'll come back to this in a minute. Is that if alpha is a bra, it acts on ket vectors psi like this and produces a complex number. That's what this is a complex number. Now, normally notationally, we drop the parentheses and just write this as alpha psi like so. And so it looks like, oh, I see I've got a white spot there in the way. That's going to be a problem this semester. So it looks like what you'd call a scalar product. But notice that it's not a scalar product of two ket vectors. It's actually a pairing of a bra vector with a ket vector. And later on, it does get interpreted as a scalar product, but we need to get there yet. We aren't there yet. This is just an operator alpha acting on psi, this notation for that. Anyway, with that notation, to say that alpha is a linear operator just means that it distributes over the linear combination in the obvious way. So this becomes alpha psi 1 plus C2 times alpha acting on psi 2, like so. All right. Now, bras by this definition, by themselves form a vector space. As I say, you can define linear combinations. If I have C1 alpha 1 plus C2 alpha 2, how am I going to define that? Well, the answer is you just let it act on an arbitrary ket like this, and you make the obvious definition. This is C1 alpha 1 acting on psi plus C2 alpha 2 acting on psi. And the point is this defines now the linear combination of bras. And so we see the set of bras actually forms a vector space. So the set of bras then is a vector space, and it's denoted by E star like this, and it's called the dual space. That's the name given to it. And it's also a complex vector space. So associated with every vector space E, there's a dual space E star. Now, by the way, bras in the mathematical world are usually called things like forms or covectors or dual vectors, but it's the same thing. They're linear maps that act on vectors and produce scalars. Okay, now, in the case of finite dimensions, if the vector space is finite dimensional, one can show that the dimension of E star is equal to the dimension of E. They have the same dimension. And that means that, let's see, I think my light is getting dim here. Let me see if I can, there, good. That's better, isn't it? We do it that way. In finite dimensions, the dimension of the dual space is the same as the dimension of the original space. In infinite dimensions, they're both of them are infinite dimensional. Okay. Now, so that's the basic idea of the dual space. Now, to proceed, I need to introduce the scalar product or the metric into our Ket space. We do it this way. This is following the usual mathematical procedure of taking an object and then adding one layer of structure upon
Sorry.
another. Yes, go ahead.
In infinite dimensions, do they have the same cardinal?
The details
Or it could be different infinites?
let's talk about that later. The details, this gets into the details of functional analysis, and it has to do with domains of definition and things of that sort. But where I'm going with this is that Hilbert spaces, as an infinite dimensional space, have the nice property that many of their mathematical properties are the obvious generalizations of what works in finite dimensions. And this is going to be an example of that, is that in a Hilbert space, although the space E is infinite dimensional and E star is also infinite dimensional, they both have countable dimensions. And Hilbert's, one of the properties of Hilbert space is that it has a set of bases that are countable. And so does E star. In fact, they're isomorphic to one another. They can be made isomorphic to one another. I'll get to that in a minute. This is part of the way of justifying the use of finite dimensional intuition in infinite dimensional spaces, which works for us, fortunately, in quantum mechanics, because it means we don't have to take a course in functional analysis to do real quantum mechanics. All right. So anyway, the dual space and the original space are, if finite, are of the same dimension. Now let me move on to another subject, which is that of the metric. The metric, which I'll call G, we'll define this as a map. And the G is a map that takes two copies of the Ket space, which I'll write as E cross E, and maps them into the complex numbers. And what this simply means is that G acts on a pair of Ket vectors, let's call them psi and phi, two of them like this, and produces a complex number. That's all it is. But to be a metric, there's certain properties that this G function, it's a function of two vectors, basically, a complex valued function of two vectors. But this G has to satisfy certain properties in order to be a metric that is suitable for our purposes. The one of them is, the first property is that G is linear in the second operand. And what that means is that if I take G with the first operand being psi, but the second operand being replaced by a linear combination of phi's, like this. And this is given by C, the obvious linear combination, C1 times G acting on psi comma phi 1 plus C2 times G acting on psi comma phi 2. All right. The second property is that it's antilinear in the first operand. And this means the following. Let me get some space here. This means the following. It means that G acting now will replace psi by linear combination, C1 psi 1 plus C2 psi 2, comma phi. This is equal to C1 complex conjugate times G acting on psi 1 comma phi plus C2 complex conjugate times G acting on psi 2 comma phi. When we say that something is antilinear, what we mean is when it acts on a linear combination of vectors, you need to complex conjugate the coefficients before letting the operation act on the vectors themselves. That's what this is. So those are two properties of G. The third property is this. The third property is what you might call the symmetry property, sometimes called that. And the third property is this, is that if I take G acting on two vectors psi and phi, and if I reverse the order, phi psi like this, the answer gets complex conjugated. And then finally, the fourth property is the positive definite property. And it says that G acting on the same vector, psi psi, both slots being the same. Now by property 3, this quantity G psi psi is real. But it's not only real, it has to be non-negative. And moreover, it equals 0. The answer is equal to 0 if and only if the vector psi vanishes. This is what we mean by positive definite property. So these are the properties that a metric in a complex vector space, positive definite metric, has to satisfy. And the metrics that we impose on our spaces do this. Hilbert space does this.
I had a question.
Yes.
I thought you said the vector psi equals 0 is not part of your Hilbert space.
Oh, no, it's a vector space, so it includes a 0 vector. When did I say that?
Oh, but if it includes a 0 vector, your Hilbert space is supposed to have been have non-zero norm, right? Or is that fine?
Oh, yeah, let's see here. Yes, I see what you're saying. Let me think about this. I shouldn't have said it that way. Not zero. No, I didn't. Did I say it that? I didn't mean non-zero norm. It has a finite norm. I said it was less than infinity. I'm not sure what came out of my mouth, but I think I wrote down less than infinity. And what that means is that the norm is finite. 0 is okay. I mean, to be a vector space, you have to have the 0 vector.
Okay.
Is that clarified? Okay, good. All right. So these are the postulates of a metric now. All right. So so let's take our metric and let's write it down as let it act on two vectors, psi and phi, like this. And for psychological purposes, let's regard the psi vector as being fixed and the phi vector as being variable. Now, if we do this, then you see what we have is, since the G is linear in the second operand, what we've got is and the answer is a complex number. We've got a complex valued linear mapping from vectors into complex numbers. And that, by our definition, is a bra. So therefore, there's some bra here. Let me call it alpha like this, just to give it a name, acting on phi. This defines alpha. Right? Now, on the other hand, it's obvious that the bra alpha depends on the choice of the fixed vector psi that we chose. So let's do a change in notation here. And instead of just calling it alpha, which is kind of a generic notation for any old bra, let's replace it by this notation and write it as bra with a psi symbol in it. The original psi is a vector in the original vector space. By putting a psi in here as a bra, what we mean is that this is the bra which is connected with that vector through this formula. And if we do this, and we have to change that notation, and this just becomes psi phi. Now you see what we've got is we've got the scalar product of two vectors is given by the usual notation like this. But we use this scheme here, this trick, in order to convert a vector into a dual vector, and then we form the pairing, and that amounts to the scalar product of two vectors. So this is a change of notation then on this metrical operation, and it simplifies the notation. Now we can talk about the scalar product of two elements of E, and not just scalar products of E and E star, you see. That's what the metric does for us. Now, let me make sure I'm not skipping something here. Yeah, okay. So now this notation is simpler than before. So let's go back and rewrite the postulates for the metric in this new notation. As far as number 1 and 2 is concerned, it looks like this: is the scalar product of psi with phi. I'll just indicate it schematically here, is antilinear in the first operand, and it's linear in the second operand. We'll just remember that. As far as property 3 is concerned, it's the symmetry property. It says that scalar product of phi with psi, or psi with phi, is equal to the same thing in the reverse order, but complex conjugated. And the fourth property says that psi with itself is greater than or equal to 0, and that it equals 0 if and only if psi is equal to 0. and this is a somewhat abbreviated but equivalent statements that way of defining the metric on the Hilbert space. So our Hilbert space will have these properties. All right. Now let me turn now to operators, linear operators or other operators that act on our Ket space. We're developing the mathematics of the Ket space, as you see. So let's talk about operators. There's two kinds I want to talk about. Both of them are mappings of the Ket space onto itself. If I have a linear operator, let me call it L, it maps the Ket space onto itself. Then it has the property that if I let it act on a linear combination of vectors, C1 psi1 plus C2 psi2, I get C1 times L acting on psi1 plus C2 times L acting on psi2. That's what we mean by a linear operator. However, in quantum mechanics, we also need to consider antilinear operators. Let me call one of those A. It is also a mapping of the Ket space onto itself. And if I let A act on the same linear combination, what comes out is C1 complex conjugated times A acting on psi1 plus C2 complex conjugated times A acting on psi2. As I said earlier, an antilinear operator complex conjugates the coefficients of a linear combination. Now in quantum mechanics, as you know, linear operators are associated with physical observables. And there's a lot of them. We'll see a lot of linear operators. Antilinear operators are also associated with physical operations, but the only one that we're going to consider in this course is time reversal. And we'll come to that later on, time reversal. And since I'm going to defer that until later on, I'm going to forget this for now, the antilinear operators. And let's just hope we can read that red ink. And let's just say that for the rest of this discussion tonight, we're going to be talking about about only linear operators. Even if I call them A now, they're just ordinary linear operators. So let's go down here and talk about them. Okay, so what can we say about them? Let's see. Let's see here. Let's see, what am I trying to do here? Oh yeah, right. So here's the first thing I want to say. Let's suppose we're given a linear operator A, as usual, maps our Ket space into itself, and I'll write it out to be explicit, emphasize that it's linear. It turns out you can define a corresponding operator that maps the dual space into the dual space. And it's not really the same operator because it has a different range and domain. Let me call it A tilde to distinguish it. This is also going to be a linear operator. But it turns out to be possible to, if you know what A does to Kets, it turns out it's possible to say what an associated operator does to bras. And here's how it works. If let's say psi is a bra psi like this is a bra, we will denote the action of, we move up and make space here. We will denote the action of A tilde on that by writing the bra first and the A tilde to the right of it. This is supposed to be another bra. Now, how do we define this? Well, being a bra, it's got to be a map that maps Kets into real numbers. So let's let it act on an arbitrary Ket, let's call it phi like this. And what shall the answer be? Well, this is the definition. The answer is this, is that it's psi on the left, and then that's, of course, the bra itself, and that acts on A phi, like so. This defines A tilde, you see? We define A tilde this way. All right, and you can easily show that this is a linear operator on bras, all right? Now in this business, it gets tired to write the tildes all the time, so most people leave them out, thereby confusing an operator that acts on one space with an operator that acts on a different space. This is called abusive notation, and we do it all the time. But if we do this, and you can see the resulting formulas after I scratched out the tilde, amount to just rearranging parentheses and saying the answer is the same. And if that's the case, why don't we just drop the parentheses? And if we do, then we get this formula that says that psi A phi is equal to psi A phi, like this. It doesn't matter. It doesn't matter whether we consider A acting to the left or whether we consider A acting to the right. The answers are the same. And this is one of the properties of now A acting on bra. So this is the definition of A acting on bra vectors, linear operators being promoted and other operators that act on bras. All right, now, here's an interesting linear operator that we can talk about. Let's say that alpha is a ket and let's say beta is a bra. Let's put them adjacent to one another like this. By putting them next to one another, this implies what's called an outer product. And what the outer product does is that it maps a ket and a bra into an operator. So alpha beta outer product like that is an operator, and we need to define what it is. We define it this way by allowing it to act on an arbitrary ket. And the answer then is this is alpha times the scalar product of beta with psi, like so. Beta with psi, of course, is just a number. And so the answer is proportional to alpha, which is a ket, so the answer is a ket. This is an operator that maps one ket psi into the total answer, which is another ket. That defines the operator outer product alpha outer product beta. Now, if I have a bra, let's call it phi, like this, then this operator, of course, has an action from the right on the bra. And write it this way as alpha beta, like so. And what is this equal to? Well, it's equal to the obvious answer. It's phi scalar product with alpha times bra beta. This, however, is not a definition. It can't be a definition because we already defined what the outer product is. So we can't define it twice. Rather, what this is this is theorem that follows from the definition. And it's easy to prove, except for that you have to keep track of, logically speaking, what you're talking about and think it through. So I'll leave it as an exercise for you to do this to show that this result follows from the earlier formula. But you can see the formula itself is kind of obvious. It just means, again, dropping parentheses. All right, but in any case, that's the outer product, which is quite important. This, of course, appears in resolutions of the identity. For example, 1 is equal to the sum on n, like this, sum on n, when the n and n form an orthonormal basis. And I'm not going to cover that in the lecture, but you can read about that in the notes. So this is one reason why I'm bringing up outer products, because they appear there. It's a special kind of an operator. All right, now, the next topic is Hermitian conjugation. Did I say this earlier? If the dual correspondence is what maps kets into bras. It maps a psi into ket psi into bra psi through the means of the metric, which I explained earlier. We bring this down so you can see better. This is the dual correspondence. By way of notation, I'm going to write this way with a dagger. We say that the psi bra, which is the image of psi ket under the dual correspondence, is given by psi ket with a dagger. The dagger here then is a notation for the dual correspondence. Now, in an infinite dimensional space, there's a question about whether the dual correspondence is invertible. And this is a student asked me a question about that earlier. It turns out that for Hilbert spaces, with this extra structure of Hilbert spaces, there's a nice answer, which is the dual correspondence is invertible. The image of this, is it's a one-to-one on the image, on its image. So there's an inverse of this. And that means that there's a DC inverse, which takes bras and maps them into kets. And moreover, it's the inverse of this. If I indicate the inverse with the same dagger notation, then I get this formula that says psi double dagger is equal to psi itself. So this is a way of defining the dagger notation. It's a way of converting kets into bra. This defines the dagger on not only kets, but also in bras. If you dagger a bra, by dagger a bra psi dagger, just turns it into the corresponding ket. So these formulas define the dagger notation on both kets and bras, and it's just the dual correspondence and its inverse and flips them back and forth. Now, it turns out, however, that it's also possible to define the dual correspondence on operators. So if I'm given a linear operator, all my operators are linear at this point, that maps the ket space E into itself, like this. What I want to do is to define an operator, which I'll call A dagger, which maps the ket space, also maps the ket space E into itself. They're both linear. The definition proceeds like this. If I want to know what A dagger is acting on a ket psi, then here's what I do. I first of all use the dual correspondence to convert psi into a bra. Then what I do is I take the original operator A and I let it act on the bra from the right. We know how to do that now. That creates another bra. And then I take the whole result and I dagger it to convert back into a ket again. The first step of taking psi into psi ket into psi bra is antilinear, but multiplying by A on the right is a linear operation. Then when I take dagger, it's the second antilinear operation. So overall, there's two antilinear operations. And the result is that A dagger acting on psi is now linear. It's a linear operator. Anyway, this can be taken as the definition of it.
Excuse me.
Yes, question.
Yeah. So you said that the double adjoint of the bra is, oh, I'm sorry. I misread something. I just saw the double adjoint and then the adjoint below, but never mind.
Is it okay?
Yeah, I think it's okay.
All right. So let's take this definition of the Hermitian conjugate of an operator and let's play some games with it. Let's this is kind of a complicated looking bra over here. So let's just make some shorthand for it. Let's call alpha as a bra is equal to psi psi bra right multiplied by A. Then this right hand side here becomes bra alpha dagger, which we know we can write as ket alpha. Now then, let's take this whole equation over here and let's multiply on the left by a bra phi, like this coming through on the left-hand side. Let's do that multiplication. And so what we get is phi, A dagger psi, like this on the left-hand side, is equal to phi scalar product with alpha over here. But that's the same thing as alpha phi complex conjugate by the postulates of the metric. And now plugging in for what alpha is here into that slot right there, this becomes the same thing as psi A phi like that complex conjugated. And if we compare the two sides of this formula we just derived, what we see is the complex conjugating the matrix element reverses the order and daggers everything. So the ket psi goes in the bra psi, which is a dagger of it. The A dagger goes into the A, and the phi goes into the phi bra goes into phi ket, which is its dagger. If we generalize the complex conjugation of a complex number just to declare that it's the same thing as the dagger, we'll now define what the dagger does to just ordinary complex numbers and declare that it's the same as ordinary complex conjugation. If we do that, then we get a rule which is very useful. It's one of the main reasons the Dirac notation is useful, is we get it. So this thing that you see becomes the same thing as the dagger of this matrix element, the whole thing here. We get a rule, which is that if you take any product of kets, bras, operators, the products can be of the form of inner products, which is the same as a scalar product. Phi psi is called an inner product. Or it can be an outer product, which I talked about earlier, like this, in which the answer is not a number, but an operator. It can be these types of products. It can be operators acting on vectors. It can be operators acting on kets. It can be multiplication by complex numbers. Anything you can put together with those operations, as long as it's meaningful. If you want to take the result and dagger it, you get the answer by reversing the order of the operations and daggering all the constituent elements. So I'm sure you're familiar with this rule, but I've just illustrated how this works out in this particular case here. And there's several more examples that are implicitly contained in what I've done so far. All right, in any case, we've now defined Hermitian conjugates of operators. All right, now let's see here. By the way, let's see, I can't read my handwriting here. Yeah, that's outer product. Oh yeah, Hermitian conjugate. Okay, so now that we've got that, let's make some definitions which you're very familiar with. So we'll say that A is Hermitian if A is equal to A dagger. A is anti-Hermitian if A is equal to minus A dagger. And we'll say U is unitary if u dagger is equal to u inverse, i.e. if u dagger u is equal to u dagger is equal to I, is equal to 1, the identity operation. So these are just
Sorry,
definitions.
how are these called? The last one?
How are they called? Did you say called? U is unitary.
Yeah, their name.
Yeah, so it's Hermitian, anti-Hermitian, and unitary. That's the three cases are being defined here. You've no doubt seen these before, but I'm going over them here. All right. By the way, in the mathematical literature, it works something like this, is that on a finite dimensional space, mathematicians prefer to talk about something that's called self-adjointness. On a finite dimensional space, a Hermitian operator and a self-adjoint operator are the same. But infinite dimensions is where you start to draw your paycheck and do real work. And in infinite dimensions, they aren't the same, and not necessarily. And it has to do with the domains of definition and details like that. And I'm going to gloss over that, as does almost all of the physics literature on this. And we just talk about Hermitian and anti-Hermitian operators. But if you ever encounter a mathematical paper, expect to see discussions of self-adjointness. All right. Domains are important in being precise about any of this operator stuff. Now, this, of course, is important, as you know, in quantum mechanics, because the physical observables are associated with Hermitian operators, and we'll get to that in a little while. But right now, I want to turn to the spectral properties of operators. So let me just put this here as the title of this page: spectral properties. By spectral properties, we're referring to the eigenvalues and so on, and eigenvectors of operators. So the basic story is this: is that in finite dimensions, the issues surrounding spectral properties, meaning eigenvalues and eigenvectors, are fairly straightforward. And they're probably also something that you've learned about in linear algebra courses and seen also lots of examples in quantum mechanics and other areas of physics where one carries this out.
Sorry to interrupt. I think I saw somebody with their hand up.
Yeah, so excuse me, if you're raising your hand, don't do that because I can't see you. It's best if you speak up. Just speak up and say question. That'll work. So is there a question?
I'm good now, thanks.
Okay, all right, false alarm. Okay. So let's talk about spectral properties. So spectral properties in infinite dimensions are much more intricate and subtle than they are in finite dimensions. So let me, on the other hand, again, in Hilbert spaces, in some cases, the situation regarding spectral properties is an obvious and simple generalization of what happens in finite dimensions. Not always. We need to be aware of when that's the case. So let me begin by talking about finite spectral properties in finite dimensions. And it works like this. Let's suppose we've got a finite, I'll call the space E, the vector space E, but it's now understood that it's finite dimensional. And let's suppose we've got an operator, a linear operator that maps E into itself. We start by making a bunch of definitions. If A acting on a ket U is equal to lowercase a multiplying ket U, where lowercase a is a complex number, and ket U is a non-zero vector in the ket space like this. Then we have a lot of definitions. We say that a, lowercase a, is an eigenvalue, of the operator A. We say that ket U is an eigenket of the operator A, like this. On the other hand, if I have, let's say, a bra V multiplying A on the left like this is equal to lowercase b times bra V like so, where now B is a complex number and bra V is non-zero, then we talk about B being a left eigenvalue, and we talk about bra V being an eigenbra. And the original eigenvalue, if you want to be perfectly clear about it, we could call that a right eigenvalue just to distinguish from the left ones if you want to do that. All right. Also, we will say that the operator A is complete if there exists an eigenbasis.
Sorry, in the first definition,
Yes.
you wrote that cat isn't equal to the space.
I don't
Is
mean,
that what you mean?
no, I thank you for pointing it out. I don't mean that. It's not equal to
Okay,
zero.
thank you.
And we normally, when we talk about eigenvectors or eigenkets, we require them to be non-zero because if it were zero, this would be satisfied for all values of A, and that's not very useful. So eigenkets are eigenvectors are normally required to be non-zero. All right, now we also say that A is complete if there exists an eigenbasis, and what an eigenbasis means, i.e., it means a basis. Just write it out in words. I'll just say it in words. It means a basis, all the basis vectors of which are eigenvectors corresponding to some eigenvalue. So that means you can gather together somehow a collection of what if n is the size of the space here, a collection of capital N linearly independent eigenvectors of the operator A. All right, so that's completeness. That means that an arbitrary vector can be expanded as a linear combination of eigenvectors of the operator. Here's another definition. Let's let AU is equal to lowercase au, where u is non-zero. In other words, that's a way of saying that lowercase a is an eigenvalue of the operator capital A. Then what we define is what I'll call the definition is this. This is the definition. We define what we call the eigenspace of A corresponding to eigenvalue lowercase a is equal to the set of vectors UNU, UNE, such that AU is equal to lowercase au. Now you see the zero is allowed. And this is basically just creating it's really a vector. So this is a vector subspace. We can denote this, I'll call it E sub A if you like. It's the vector subspace corresponding to eigenvalue A, but just give it a notation. And it is the subspace which is spanned by all the eigenvectors. It contains all the eigenvectors, including zero in this case, with the corresponding eigenvalue. And it's easy to show that's a vector subspace of the original space. So it has some dimensionality. So in this case, the dimensionality of the subspace E sub A is, we'll call this the order of the eigenvalue. And you're quite familiar with the usual notation that if the order is equal to 1, we say the eigenvalue is non-degenerate. And if it's more than 1, we say it's degenerate. That's very common terminology. All right, so these are all a bunch of definitions that apply for essentially eigenvalues of finite matrices, because this is all in finite dimensions. Now, it turns out that even in finite dimensions, not all operators are complete. You might think they are. Some physicists I've seen go around assuming that every matrix or operator they ever encounter has a complete eigenbasis, but it isn't true. And a simple example is this: if I take the matrix 0, 1, 0, 0 like this, rather innocent looking matrix, this matrix has an eigenvector. It's the vector 1, 0. And if you do the matrix multiplication, you find the answer is 0, 0. So this is A acting on U equals 0. And so you can see the eigenvalue is equal to 0 here. It turns out this is the only eigenvector of A, apart from scaling. This is the only eigenvector A has. And so there are no other eigenvectors. And so its eigenvectors do not span the space. There is no eigenbasis, and therefore this A is not complete. And that works even for a 2 by 2 matrix, or that doesn't work even for a 2 by 2 matrix.
Professor, is it the same thing to be complete and have full rank?
No.
No.
No, because I could put, how about this one, 1, 1, 0, 1 here. Now the eigenvalue A has been shifted. It's now equal to 1, but the eigenvector is the same. And it's still the only eigenvector there is.
Okay,
Now, on the other hand, if A is Hermitian, then there are massive simplifications, which I'll list here, massive simplifications. One of them is that let's see, did I finish all my definitions? No, I'm sorry. I want to give one more definition to this list. Here's what this is. Before I get into that, let's do one more definition. What I'll call the spectrum of the operator A. The spectrum of the operator A briefly is just a set of all eigenvalues. So it's a set of all complex numbers A such that AU is equal to lowercase au for some non-zero u. This is just a complicated way of saying that it's the set of the eigenvectors. But the spectrum of A is a subset of the complex plane. If I plot the complex plane of real and imaginary parts, if you're in finite dimensions, the spectrum is going to be a collection of points in the complex plane looking like that. We'll see the spectra get more interesting in infinite dimensions, but this is the basic idea of it. All right, so anyway, that's another definition that I wanted to make. Now, to go back then to where I started a minute ago, is that if A is equal to A dagger, there are massive simplifications. Oh, by the way, the spectrum, we could talk, this is what I've written out here is actually what you might call more properly as a right spectrum, because I'm dealing with eigenkets. There's also there's a left spectrum, which deals with left eigenvalues and eigenbras. And by the way, for an arbitrary linear operator, there's no simple relation between the left spectrum and the right spectrum. If you have the right eigenvalues, it doesn't easily anyway, it doesn't help you determine what the left eigenvalues are, or the eigenbras and eigenkets are not related in any simple way from an arbitrary operator. However, if the operator is Hermitian, then there's massive simplifications. The first one is that the eigenvalues are real. And that means that the spectrum is a subset of the real axis in the complex plane. The second one is that the left eigenvalues are equal to the right eigenvalues. So the two spectra left and right are the same. Also, the eigenbras are equal to the dagger of the eigenkets. So if you solve the right eigenvalue problem with the usual eigenvalues and eigenkets, you just do the daggers and you get the eigenbras, and the eigenvalues are identical. That's for a Hermitian operator. Let's see, here's a third property, is that the eigenspaces are orthonormal to one another, or excuse me, are orthogonal, mutually orthogonal. So for example, if I had a three-dimensional space with a Hermitian operator acting on it, and it had two distinct eigenvalues, one of whose eigenspaces was 1D and the other was 2D, I can visualize the eigenspaces as something like this. Here there's a two-dimensional eigenspace like this, let's call it E1. And then orthogonal to that is the other eigenspace E2. And somewhere here's the three-dimensional axes for the vector space. This is what it looks like. And these are orthogonal to one another. Eigenspaces are mutually orthogonal. The fourth property is that A possesses, can I spell it up to you? It possesses an orthonormal eigenbasis. Orthonormal eigenbasis. That's to say a set of eigenvectors that are mutually orthogonal to one another, the normalized vectors, and they span the whole space. And the fifth one, which follows trivially from number 4, is that A is complete. So Hermitian operators in finite dimensions are always complete, and they always possess an orthonormal eigenbasis. If you were going to transfer finite dimensional vector space intuition to the infinite dimensional spaces that occur in quantum mechanics, you might be tempted to assume that these two properties work there as well. And in fact, the actual situation is more complicated than that. And that's something I won't probably won't be able to get to tonight, but this will be the first topic we'll take up next time, is what happens, how this changes in infinite dimensions. Actually, the stuff that I'm giving you here is really review of stuff you should have seen in some course somewhere, because these properties that I'm listing here are really the outcome of these standard theorems that you can diagonalize a Hermitian matrix by means of a unitary transformation. All right, in any case, let me go through some of these properties that I've listed here, and let's prove some of them. So the proofs are straightforward. If I take number one, that the eigenvalues are real, it works like this. If I have A acting on U is equal to lowercase a acting on U, and then I take the Hermitian conjugate of this equation, what I get is U A dagger, taking the conjugate of that, but that's equal to U A because we're assuming A is Hermitian. That's equal to A star bra U over here on the right-hand side. I'm leaving open whether A is real or not. Now, if we take the first equation and multiply on the left by bra U, and the second equation and multiply on the right by ket U, like this, coming in from this side, this one comes in from that side, then the first equation is U sandwiched around A is equal to lowercase a times UU. And the second equation gives me U sandwiched around A is equal to A star times UU. And so if we subtract these two, we get A minus A star multiplying UU is equal to 0. Now, eigenvectors, as I explained, are not supposed to be 0. So we can cancel that term and you get A is equal to A star, and thus we see the eigenvalues are real. And so that's the proof of number one. I won't bother to prove number two because it's straightforward, and I'll just let you do it. Number three, the eigenspaces are mutually orthogonal. Let's do that one. Let me rephrase it in a slightly different way. The rephrasing would be to say that if I have two eigenvectors of Hermitian operator A, then either the eigenvalues are distinct, or else the eigenvectors are orthogonal to one another. So, did I say that right? Yeah. So let's prove the theorem. It works like this. Let's suppose
question.
Yeah.
Sorry, could you just repeat that sentence you just said?
Yeah, let me think through it again, make sure I get it right. If the eigenvectors belong to distinct eigenvalues, then they're orthogonal, as you see from the picture here. If I got a vector in this E2 space and another one in this E1 space, then they're going to be orthogonal because the subspaces are orthogonal. If they lie in the same space, then there's no requirement. I could have two vectors here that are not orthogonal in the E1. That's okay. But then the eigenvalues are identical. So either the eigenvalues are identical, or else the vectors are orthogonal. I think I said that right. That's the statement.
Okay, thanks.
All right, so let's let A acting on U1 give me A1 times U1, and let's let A acting on U2 gives me A2 times U2. And by now we know that the A's are real. If I multiply the first equation by bra U2 on the left and the second one by bra U1 on the left, and the first equation becomes U2A U1 is equal to A1 times U2 U1. If I multiply the second equation on the left by U1 and then take the Hermitian conjugate of both sides, what I get is on the left is U2A U1. And on the right-hand side, I get A2 times U2 U1. I didn't star A2 because I know it's real. But I kind of skipped a step there. I hope that's clear. The left-hand sides are now the same. So if I subtract them, what I get is A1 minus A2 times U1 scalar product U2 is equal to 0. And thus either the vectors are orthogonal or else the eigenvalues are equal. And that's the equivalent to the statement that the eigenspaces are mutually orthogonal. This is kind of a roundabout way of stating the matter. It's geometrically, it's more clear to draw the picture or to say it this way. And I think that's a better way of thinking about it, is that the eigenspaces of a Hermitian operator are mutually orthogonal spaces. Now then, if we've got that, if we've got a set of mutually orthogonal eigenspaces like this, some of them may be multidimensional because of degeneracies. That's how I drew it here. There's a twofold degeneracy here in a 3D space. If a space is non-degenerate, we just choose a unit vector in that space, and that gives us a basis in that subspace, that 1D subspace. If it is degenerate, we just choose an orthonormal, but not like I drew it here. We choose an orthonormal basis in this space. Let's draw it like that. In this space, there's lots of ways of doing that. And now we've got an orthonormal basis in that space. Let's do this for all the eigenspaces. Then what we have is a set of orthonormal unit vectors that cover all of the eigenspaces. And because between spaces, they're automatically orthogonal and orthogonal within the spaces. So then now it's overall orthogonal in the whole space. Now the question is then, do they span the whole space? Because if they do, then we've got an orthonormal basis, and that is means that the operator is complete. That's in fact what we're saying here in item number 4, that it possesses an orthonormal eigenbasis. The easiest way to argue that A possesses an orthonormal eigenbasis is just to refer to the theorems that you know about diagonalizing Hermitian matrices by means of unitary matrices. If you just look at that, it's the columns of the unitary matrix that do the diagonalization are an example of a orthonormal eigenbasis, and so that's the easiest way of proving number 4 or proving it. In any case, what that means is that A is complete. And what that in turn means is that if we look at the eigenspaces, the eigenspaces actually fill up the entire Hilbert space of the problem. There's a nice way of stating that fact, and it looks like this. It is to say that the A is complete. So let's do it this way. Let's let En be the eigenspace corresponding to eigenvalue An. Lowercase a sub n. Then A is complete. This is a way of writing it. A is complete if the entire Hilbert space is equal to a direct sum of E1 direct sum, E2 direct sum, and so on like this out to the last one, E sub the final one, whatever it is. These correspond to, there's one of these subspaces for each distinct eigenvalue. They may be multidimensional. And what this direct sum means, it's a way of taking subspaces of a vector space and then combining them together to make a larger space. E1 plus E2 is defined as the set of linear combination of it's a set of all possible vectors that can be made of linear combinations of the two constituent spaces. So in this picture here, E1 plus E2 is the span of that 2D space combined with the span of that orthogonal 1 space, giving an overall 3D. So in any case, I'll say more about the direct sum in the next lecture, but this is a neat way of stating the completeness property, which is a little closer to the geometrical reality of it. This is a set of mutually orthogonal eigenspaces. Okay, so we're out of time. I have a couple of comments to make. One is that I think this semester what I'm going to do in cases in which I've finished one lecture in the middle of a topic, which I need to review to get going again for the next lecture. I think I'm going to start a few minutes early in order to do the review material, just to bring us up to where we left off in the last lecture. And I won't start any new material until the official start time, which in Berkeley means for us would be 6:40, 10 minutes after the 6:30 nominal start time. So I hope that's okay. We'll do, if need be, we'll do a little review before the actual start time. So that's all for tonight. Are there any questions about the lecture?
Yeah, so just to make sure that I understood it, this last part with A complete, this only applies for finite dimensional vector spaces, right?
So what I'm doing is I'm going over the situation for finite dimensions. And
okay, yeah.
in an outline, you should actually know all of this already, because this has to do with diagonalizing matrices, and you've seen this stuff before.
Yeah.
But I'm doing it first because I want to contrast with what happens in infinite dimensions, where there's new phenomena that occur. In particular, in infinite dimensions, you get the continuous spectrum. You also get the fact that some Hermitian operators are not complete anymore. So there's issues that arise in infinite dimensions. That's the first topic to be addressed in the next lecture.
For sure.
All right, good. Any other questions?
I had a question. So we spoke about non-normalizable vectors at the beginning of the lesson. What space do these non-normalizable vectors live?
Yeah, good question. Well, they wouldn't be in the Hilbert space, would they? But if they were wave functions, you could write down the wave function that was not normalizable. So it depends on the problem. I mean, if I'm talking about if the Hilbert space is the only universe I'm dealing with, and it doesn't have any concrete realization, such as, you know, a space of wave functions, then there are no vectors with infinite norm. They don't exist. I mean, you can certainly form limits. You can think about, you know, a limit of a sequence of vectors in Hilbert space where the norm goes to infinity, but that limit is not a member of Hilbert space. If those were wave function spaces, that limit might very well exist. Probably, usually it would be. Does that help? I mean, it depends on, you need to define what your spaces are in order to make sense of these things.
Sure. So in your Ket space itself, your momentum operator just doesn't have eigenfunctions?
Yeah, I'm going to get to that next time. It has no eigenfunctions in Hilbert space. So not only is it not complete in that sense, it isn't even it doesn't even have even a single eigenvector, much less a complete set. Any other questions?
I think Rohith asked in the chat, what space does the outer product live in?
Excuse me?
It was asked in chat, what space does the outer product live in?
Well, the outer product is a complex number, so it lives in the complex numbers.
Right, isn't it an operator?
Yeah, so I know we have a chat feature, but I generally won't see it. It's better if you speak up, and then of course everybody else can hear you.
Wait, sorry, isn't the outer product an operator?
Oh, I beg your pardon. He said outer product. I was understanding inner product. Oh, what space does that live in? So the question now is, if I have, so does this have to do with normalization then? So what space does the outer product? Well, it lives in the space of operators. You know, I'm defining here as an operator that maps the Ket space into itself. And I'm glossing over a lot of stuff. I think people that know functional analysis are tearing their hair out at this point. Because if you have an operator, you know, that acts on a Hilbert space, let's say, it may well be that its action is not defined on some vectors. Or if it's wave functions, it may be that an operator takes a wave function with a finite norm and maps it into one that it's of infinite norm. This is in fact very common in quantum mechanics. Hamiltonians do this, so does the momentum. These operators are called unbounded, and dealing with unbounded operators is a big issue in the precise mathematical treatment of these problems. In this course, I'm going to tend to gloss over that because I don't think it affects most of what we need to do in a practical standpoint. Any other questions?
In the definitions of the metrics, what is the reasoning behind it being positive definite, like greater than zero?
You know, metrics don't have to be positive definite. The Minkowski metric in special relativity is not. You know, you get light-like and space-like vectors that have one is positive norm and square norm, the other is a negative one. So in the world of metrics, they don't have to be positive definite, but they are for a Hilbert space. And a positive definite metric roughly corresponds to the notion of distance. In fact, it can be used to define a distance, and it is used that way in Hilbert space. This is how we frequently talk about the distance between two wave functions. It's the integral of, you know, psi1 minus psi2 squared. That's the square distance. So let's just say that positive definite metrics are useful in a lot of applications, and that's what we use here. Quantum mechanics gave it to us. I think there's deeper answers to this question if you get into you know, quantum field theory and curved spacetimes and so on. There's as I say, there's deeper answers to this, but anyway, for quantum mechanics, this is the best I can do, I think. Hope that helps. It's basically a generalization of just the usual metric we have in 3D.
Thank you.
Any other questions? There was something else I wanted to add, but now I forgot what it was, so I guess I'll have to wait. Okay, well, if there's no other questions, then I'm going to close the screen sharing here, and I'm going to stop the recording. Oop, no, press the wrong one. Let's see, where's the recording? Oh, here we go. Stop it. Stop recording.